Okay, great. All right, so my name is Nicholas Majeski, and as you might recall, I'm doing extreme event forecasting on the Wabash River Basin. So I'll just go through a little bit of, I'll just recap on my project. So Wabash River Basin is the largest northern tributary to the Ohio River. It's about 90,000 kilometers squared over Indiana, Illinois, and Ohio. And we have a few observed climate properties. It's about 11.3 degrees Celsius on average, and about 122.7 centimeters of precipitation per year. Okay, so the extreme event of interest that I'm trying to model is drought. So this is defined as a prolonged period of below average water availability. And I'm looking to model two types of drought. That would be soil drought, which would be below average availability of soil moisture, and then also stream flow. And as I covered before, if we can model the event of drought or flooding, one of those extreme events, it might help us to better prepare for such a scenario and lessen the economic impact. Okay, and then going over the data again. So the data set features 31,046 time steps, which are day-by-day measurements. And each of those day-by-day measurements has entries for all of the different sub-basins. So each of these polygons here in the image you're seeing is one of the 1,276 sub-basins. And so, excuse me, for this problem, we have for all these time steps and for each of the sub-basins on one of those time steps, we have the precipitation, the maximum and minimum temperatures. And what we'd like to do is taking those three inputs, we would like to predict the stream flow and the soil water content. And we would like to do so over a span of days. So maybe if we're allowed to observe the last month, we would like to use that data to then predict what the stream flow and soil water content are going to be over the next month. So as before, I proposed an LSTM, long short-term memory recurrent neural network, to model this input and output relationship. And so far, I have trained the model, and these are my preliminary results. So yeah, for stream flow, I have this output, which is actually only the output for the very first subbasin, because you can imagine visualizing across 1,276 of those would be quite difficult. But here for this one, we can see the ground truth output in green, and then the model's actual output. And it's not doing very well. This is actually very hard mapping to learn because it is so high dimensional. And moreover, I have not trained the model for a sufficiently large number of epochs to hope to get a good match. But here are the outputs nonetheless. So this is the last year, so the number of days up to 365. And it's learning something. So that's the main takeaway, and that makes me hopeful. So it's capturing something about the stream flow as a function of the precipitation and min-max temperature. Okay, and then we have the soil water content. And again, it seems to be exaggerating the actual numbers. So if we look here, as the soil water content drops, the model seems to over-exaggerate that and seems to plummet in its predictions. So I'm not sure what's going on there. And then when it does really plummet, it just can't quite reach that range. So it almost seems like it suffers from, it can't quite catch the range of values that the ground truth has. So it may not be a complex enough function So I may need to have more parameters in the model. Okay, so on the progress I've made, as you might recall, my main pitch was to address this problem of memory, because the data features so many time steps, and each time step has extremely high dimension of all the subbasins, and then 3 inputs, 2 outputs for each of those. For a very small number of input time steps and output time steps, I was at like 18 gigabytes of memory being consumed. So to solve that, I proposed doing data parallelism. And well, I've actually successfully implemented that. So that's the good news. And so for P processes, the time series tensor that I talked about requiring 18 gigabytes is actually split into P partitions and distributed to each of the processes. So you can see if we start the program here, process 0, the root, will actually distribute all the time series data. And then each of those processes performs its own train, dev, and test sets for training. And then they all start this, the actual training itself. So, oh, sorry about that. So they all start the training. So each one of the processes performs a forward pass, compute the error. They then perform back propagation through time to compute the gradients for all the parameters in the LSTM network. Then here's the actual communication part you need as a result of distributing this. And that is, you actually do a very simple all reduce call. So all processes sum over all the gradients in the network. So if we have, 10 different processes compute the forward pass for the batch that they're currently on, they compute the gradients for every weight tensor in the LSTM, then all of those gradients are communicated and added together. Now each of the 10 processes have the same gradient that they can then apply to the network. Okay, so yeah, once they have the gradient, they can actually update the weights, and then you just repeat for however many epochs you want to train. Okay, so there's been a few other things I've implemented on the way to this that just came out of convenience and something I would need to do in the future. So a big thing was implementing feature standardization. I used the mean removal and variance scaling standardization. I also implemented model checkpointing because, well, when you have as many, as high of dimensions for this model, you need a lot of parameters, and so training's rather slow. So it is nice to be able to save and pick up where you left off. So I've got that done. And a small thing, but very important, is model evaluation and visualization. So once I've trained to a certain point, I can have my program just load that model in and actually evaluate it on the time series data. And then I can put it out into the graphs that you saw. And then there's a small thing, I haven't really fleshed it out, but it's just some additional testing on the test set itself. And so if I have 1,000 test samples, I just went through and computed the average loss across all subbasins. And this is to kind of highlight which subbasins are harder for the model to learn. And surprisingly, well, unsurprisingly maybe, is that there in fact were some subbasins that had drastically higher error, which would suggest that the outputs for those subbasins, maybe they fluctuated a lot more than others. So those might be interesting to study in more detail. Okay, so with all that being said, this is what I have left to do. The main thing is what I'll call time series downsampling. So first of all, distributed training reduces local memory consumption to a practical margin for a sufficiently large number of processes you want to use. So with the amount of time that's left, and since this does address the problem I presented earlier on, I think I've decided to leave the domain parallelism I talked about for future work because it's quite involved now that I've researched it in more depth. And there seems to be a more important issue that I'd like to address at this point. Okay, so now that we have this model, we would really like to predict whether or not there'll be drought or whether or not there will be flood, some extreme event for a number of output time steps T out. And having talked with the other group of researchers who originally gave me this data, they let me know that to consider something a drought or a flood, we would look for above or below average water availability for at least 14 days to longer. So with that in mind, we'd like to predict the stream flow and soil water content for 14 days to an entire year. Okay, so the problem with this is that if we scale the number of time steps in, the number of time steps out to that extent, it's going to increase the model complexity quite a bit, and definitely increase the training difficulty. Certainly at 365 time steps, the gradient is going to suffer, either by vanishing or exploding gradients. So my proposed solution for this problem is we could downsample our time series data. Let's say we do it by a factor of 7. So right now it's day by day time steps. If we downsample it by a factor of 7, we could take the average over 7 days and make it a week by week data set. And by doing so, we could instead train our model to predict for time steps 2 to 52, which would certainly alleviate some of the gradient issues or make them less of an issue at least. But there are some problems with this that I'll get into now. Namely that it complicates the distribution of the training samples, as I showed before in the distributed training model. And it does result in the loss of some training samples. So here's some of the challenges. And I apologize that this is all text. When I was writing this, I thought in my mind, oh, I'll just give some examples on the whiteboard, but I kind of forgot that that's not really an option. But hopefully this makes sense. So a naive solution for downsampling the data set would be to take every window of 7 days and just take the average. And so, and doing this would be to have no overlap between the windows of 7 days. Okay, so if you do this, you're going to reduce the number of samples you have to train on by a factor of 7, which is a lot. It's about, it would take us from 31,000, roughly speaking, down to about 4,000. Yeah, which would be difficult to train on if we have that limited number of samples. However, we can actually combat this reduction of training samples factor by allowing the windows to overlap. But in doing that, there's actually some issues as well. So yeah, instead of having no overlap, maybe you just do a step of 1. So the first window is over day 1 to day 7, and then the next one is day 2 to day 8, day 3 to day 9 to 10, and so on, something like that. And that way, the actual number of training samples you lose about 7 doing that. Well, it also depends on the number of input time steps, but yeah, you don't lose nearly as much. So we can do that, but then we run into an issue because the data points that we might make now, if they overlap, they're not truly week by week. So if we give the model 2 time steps, 2 weeks, but those 2 weeks overlap, then it would really be 7 days plus another 1 day. It'd be repeating a bunch of the data, which is not a true 2 weeks, it's 8 days. Really helps if I could draw a sample on the board, but either way, that won't work. So we actually, if we want to distribute this data, we have to do it in such a way that a given process is not given any samples that have any overlap. So in other words, by having overlap in the downsampling, this actually causes our number of processes to be coupled with the downsampling factor in the stride. So when I go to implement this, there will be some relationship to the minimum number of processes I can have and the downsampling factor, which could be an issue at lower scaling. But hopefully we just scale it up and it's not too much of a problem. Okay, so that's what I'm going to do for the rest of the semester. And here's my updated schedule. So we're on week 13. This is my midterm update. And I'll start working on downsampling. I have an initial implementation, but it definitely needs to be finalized. So, and then next week, I'll just do some more testing and continue to implement downsampling. And there's some like miscellaneous features I need to implement. The main one is learning rate scheduling. So like learning rate decay and things like that certainly need to be implemented. So I'm going to work on that as well. And then for week 15, just do more testing, get my figures drawn up and write my report or my final presentation. And then week 16, I'll present. And then the evaluation plan is the same, using the train development and test sets to validate the model, or at least get an idea of how it's performing, how it's generalizing. And then also look at the memory consumption while scaling up the number of processes. It's the same, except I'm not considering a matrix representation anymore because it's just way too much data that's required to represent it in a matrix. So that's the way I've changed my evaluation plan.
So did you try any other type of networks? Just the LSTM?
Just the LSTM.
Maybe a CNN is easier for you to learn, to train.
Are you asking with regards to the performance you're seeing?
I mean, because CNN has no dependency between each layer. Maybe it's faster for you to train, but you don't know the accuracy. You don't know which one is more accurate.
Oh, yeah. Yeah, I could, well, I wanted to do initially some kind of time series model that was taking as inputs the output of CNNs. So I wanted to have a convolutional layer that preceded the recurrent neural network, or LSTM, so that I could extract some of the spatial information we're seeing here. So like this hotspot, if we want to predict the stream flow of this subbasin here, we'll probably do much better if we can capture the local data, since we see the hotspots. There's definitely something spatial going on there. But I've met with the people that gave me this data set to try and get some kind of image representation. All efforts were unsuccessful, and looking at some of the images that are available, their resolution is extremely, extremely high. And we wouldn't really have any hope of holding all of that in memory for 31,000 time steps.
Sure. And it seems that you concurrently predict the soil and the stream. You have two images, right?
Well, I don't have images coming out.
No. You show the two figures. Next one.
Yes.
Yes, this one and the next one.
It's predicting the stream flow for each subbasin and then the soil water content for each subbasin.
Are they related, or these are two independent
I mean, I would imagine that the soil water content affects stream flow.
Okay, I see.
Just because they both generally give some kind of qualitative or quantitative measure of how much water there is in a particular subbasin. But, you know, I don't have any expertise on the subject other than
Okay,
maybe LSTM. So
I see. Okay, good.
Okay.
Thank you.
Any other questions? All right. Well, thank you very much.